Good morning, IB, HLAA. I guess you could be watching this at night, so if that's the case, good evening. Today's lesson is on the Poisson distribution. The notation that you'll see for Poisson typically comes in this form. This will say a variable x is Poisson, P-O, right? So this is subscript O of lambda. And lambda is a Greek letter, and that lambda represents some kind of rate. All right, so probability that's determined by a rate in the following items. So the probability that x equals some particular value, right, is equal to e to the negative lambda, lambda to the x over x factorial. We're not going over that proof in this class. That can be found online. I can also make a proof of that if you'd like to see it. Now, what's nice with Poisson is that the expected value is actually equal to the variance, which is equal to lambda, and the standard deviation is equal to the square root of lambda. Now, some of this might be just a little too general at this point, so let's get into a few examples and see how it works. Before we get into a Poisson example, let's do a quick review on binomial. It says here in this example, a game is played where a marble is removed from a bag, the color noted, and then replaced. Just important to note that when we have replacement, we don't necessarily have to worry about probabilities changing based on a certain number of trials. Okay, so if the probability changes, that's because potentially there's not replacement or something else going on. Okay, in the bag there are red and white marbles of the ratio 3 to 5. So we could say that there's 3 red marbles to every 5 white marbles. So the ratio of white, right, would be 5 to 3 or 0.625, whereas the ratio of red would be 3 to 5 or 0.375. Okay, so find the probability that in 8 trials, at least 7 are white. So we're calling success a white marble. Okay, so we're going to call our probability P. Okay, P is going to equal 0.625, right? That's the probability of drawing a white marble at any given point. So to find the probability that in 8 trials, at least 7 are white, right, we would have to find the probability that x equals 7 plus the probability that x equals 8. Now, you could do this in a couple of different ways. One is find those two probabilities individually. So that would be 8 choose 7, p to the 7th, q to the 1st, and 8 choose 8. Right? So this would be 8 choose 7, 0.625 to the 7th, and 0.375 to the 1st. That would be the probability x equals 7. Probability x equals x is 8 choose 8, and 0.625 to the 8th, 0.375 to the 0. Now, that's labor intense. We don't want to do that. What we want to do is we want to use a binomial CDF, right? And what we're going to do is we're going to add up all probabilities from 0 white marbles drawn up to 6 white marbles drawn, which would be the following. Binom CDF. Okay, and we would go 8 trials, probability of success 0.625, up to and including 6. Right? The reason we use 6 instead of 7 is because CDF accumulates to that value. We're going to take 1 minus that. That's going to equal this probability right here, right? Where we could say that the probability that x is greater than or equal to 7. In executing that step on the calculator, we can see that the probability that we would get 7 or more marbles of white color would be 0.135. All right, let's look at part B. Without restriction on the number of selections, determine how many marbles must be chosen to ensure that the probability of having at least one red marble is 9/10. Okay, so this is an interesting problem, but they give you enough of a hint that it's doable. Okay, so let's think about this for example. Probability of having at least one red marble. Well, that's going to be 1, oops, that's going to be 1 minus the probability, and we'll call this event y, minus the probability of getting 0 red marbles. All right, so let's say y is the number of red marbles that we are selecting. Well, we want for this to be at least, to ensure that the probability, we want it to be 9/10, right? We want it to be 9/10. Okay, so the math here is relatively easy. You might not see it yet, but this is going to have a variable involved, right? We'll see that in just a moment. But if I solve for that, right, the probability that y is equal to 0, what we want to be the case is we want for that to equal 1/10, right? I just subtract 1 from both sides, divide by -1. Now our goal is to figure out how many trials need to happen in order for us to get a probability of 1/10 for choosing 0 red marbles. Okay, so let's lay this out. We kind of have an example like it above, right? Above we said we chose 0 red marbles, which meant we chose 8 blue marbles, or excuse me, white marbles. Now here I don't know how many trials I'm going to have, so what I'm going to do is I'm going to write the number of trials is n, and say n choose n, and we're going to choose 0 red marbles, and we're going to choose n white marbles, and we want that to equal 1/10. Well, the nice part about this type of problem is that n choose n just equals 1. 0.375 to the 0 just equals 1. So it really comes down to this ratio of 5/8 to the nth power, to the nth power is equal to 1/10. We got to figure that out. Now, this would be an example of a calculator allowed question, so let's go ahead and figure that out. Using the natural log, I can quickly calculate that. So I take the natural log of both sides. That leaves me with n times the natural log of 5/8, right? Because when I take the natural log of the left side, I can bring that exponent down in front, which will equal the natural log of 1/10. So I'm going to take the natural log of 1/10 and divide it by the natural log of 5/8. Okay, so when I solve, I get a value for n that's approximately equal to 4.889. Nope, 4.899. Okay, that tells me that to get at least 1 red marble 9/10 of the time, I have to do at least 5 trials. So that would be 5 trials. Clearly at n equals 4 trials, that would not be possible. We wouldn't quite reach 9/10 as a probability for getting at least 1 red marble. Okay, very interesting problem there. Let's now jump into some Poisson work. All right, here we got a Poisson example. An archer hits their target at a rate of 5 arrows per minute. Okay, so we want to take note to this rate. What is the probability that in a 90-second competition, this archer hits the target exactly 10 times, and part B, more than 4 times? So the first thing you want to do is identify the rate. The rate given in this case is 5 targets per minute. Okay, we're going to translate that lambda value to match a 90-second interval instead of minute interval. So lambda, we're actually going to say is 7.5 targets per 90 seconds. Okay, so we're going to define this variable, let's say a variable x, which will be Poisson with a lambda value of 7.5. Okay, and this is to be the number of targets acquired, actually I should say hit, in a 90-second interval. Okay. Now, that allows us to then build these following probabilities. So the probability that our variable x equals 10 can be done in a couple different ways, one of which would be e to the negative lambda to the x over x factorial. Okay, if you have a non-calculator portion of the test that you're required to work with, this would be how you do that. Or with a calculator portion, the probability that x equals 10 will be a a Poisson PDF with inputs of lambda and number of targets. Okay, and that comes out to, in either case, to be 0.0858. Okay, so that's the probability of hitting 10 targets in 90 seconds, given that said archer can hit 5 targets in 1 minute. Okay, so more than 4 times. Now, this is definitely going to be a calculator allowed question. The probability that x is greater than 4 is going to be 1 minus the probability that x is less than or equal to 3. Now, I can build probability that x is less than or equal to 3 with a Poisson CDF. So this would be equal to 1 minus Poisson, I'm probably saying that wrong, CDF 7.5 and 3. You include 3 in your CDF if you want to negate it in x greater than 4. Oh, I'm sorry, it says greater than 4, so I want this to be less than or equal to 4. Okay, so correct that, less than or equal to 4. Okay, so that'll give me the probability that you hit the target 5 or more times. Okay, so let's do a quick calculation on that. All right, so the probability that said archer hits more than 4 targets in a 90-second interval ends up being 0.86 and 7. There you go. Okay, let's look at another example. All right, cars have been observed passing a given point on a back road at a rate of 2/5 cars per minute. So I would say in this case that lambda is equal to 0.4 cars per minute. Find each of the following probabilities, or per hour it says. Okay, so that no car passes this location during a 2-hour period. So I'm going to change lambda, right? In this case, lambda will be now a 2-hour period, so I'd take 2 times 0.4, which is 0.8. Okay, and I'm going to define x in part A as Poisson 0.8. Okay, so the probability that x equals 0, that no car passes this location in a 2-hour period, will be e to the negative 0.8 to the 0 over 0 factorial. This actually comes out to be 1 over e to the 0.8. Okay, if I were to use calculator, this would be a Poisson PDF. Lambda is 0.8, and number of successes in this case would be 0. Okay, we have to redefine a new lambda in part B. And part A, you can go ahead and find that to 3 sig figs with your calculator. It says that at least 20 cars pass this location in a single day. Okay, so now what I need to do is I need to take my original lambda, turn that 1-hour rate into a 24-hour rate. So 24 times 0.4 ends up being 9.6. So lambda in our new case in part B will be 9.6. And I'm going to redefine a new variable here. I'm going to say y is Poisson 9.6. This would represent the number of cars passing this certain point in a given day. Okay, so at least 20 cars, what I would do to find this, the probability that y, and I wouldn't do this without a calculator. When you get to a point where you're doing at least or at most of the time, you're not going to have to do that without a calculator. That y is greater than or equal to 20, I would take 1 minus Poisson, and I just accumulate all of the probabilities up to and including 19. Okay, let's do a quick calculation on that one. Looks like a really, really small chance of that happening, which makes sense contextually because our rate actually tells us a lot. So if you look at this rate, this is the expected value or expected number of vehicles to pass that point for an entire day. And I'm looking at, what's the probability that at least 20 cars pass? Not likely, right? If the average number of cars that pass that spot during a given day is 9.6, then for sure 20 is highly unlikely. Okay, so part C is actually really interesting. It says that in a given 30-day month, at least 20 cars pass this location between 5 and 25 days. That we want to find that probability. Okay, so now this actually becomes binomial. Okay, it becomes binomial, and the reason why is because either cars pass this spot or they don't. So we want to know on any given day, what's the probability that 20 cars pass this location? Well, we already know it. It's 0.002, right? So this is binomial with P equal to 0.002 and Q equal to 1 minus 0.002. Okay, so what we want to know then is we want to know the probability. I'm going to write out a new variable, and Z here is going to be binomial with, let's say, 30 and P 0.002. Okay, so 30 trials, 30-day month. Okay, probability that on any given day 20 cars pass this location, 0.002. And of course, what I want is I want the probability that Z, I should rewrite that, hold on, that Z is inclusive between 5 and 25. All right, so in the context of this problem, this isn't that great. The numbers aren't going to come out to be all that awesome. But what I want to do is I want to show you how you would go about this problem, because the answer doesn't work out very nicely. What we would want to do is take a binomial CDF, all right, and we want to go from, for 30 trials with a probability of success of 0.002 up to 25, right? That'll accumulate the following probability, right? That Z is less than or equal to 25. And then I want to take away from it the probability that Z is less than or equal to 4, right? Because then that'll kind of take, imagine this is the probability, this first probability, and then I want to take away, right, even though this is discrete, I'm going to take away the first 4. Right, which leaves me with inclusive from 5 up to 25. Now this is a very informal visual, but it helps you to kind of see that. Okay, so then I would do the same thing here, binom CDF, 30.002 and 4. Right, that then gives us the probability that this particular variable is between 5 and 25 inclusive. Okay, the answer comes out to be really, really close to 0, because this number actually comes out, your calculator can't decide whether it's 1 or something else. So anyways, let's move on to another example here. All right, students sign up at a desk for an activity during the afternoon. The arrival of each student is independent of any other, and the number of students arriving per hour can be modeled by the following variable. Okay, so right here we don't know lambda, but I'm guessing we're going to find it here in this problem. All right, the desk is open for 4 hours. If exactly 5 people arrive to sign up for the activity during that time, find the probability that exactly 3 of them arrive during the first hour. Okay, so 5 people per 4 hours. So I'm going to say 5 people per 4 hours. All right, so now what it's asking us, this is our initial lambda setup, right? So what I could say if I wanted to is that lambda equals 1.25 people per hour, right? Which is kind of where I want to translate that, and you can see that because it looks like we want to find the probability that exactly 3 people arrive during the first hour. Okay, so what I'm attempting to do here is I'm going to define my variable, right? X is Poisson, 1.25 represents the number of people at the sign-up desk during a given hour. Okay. Now we want to know the probability, and that's the formal way to set this up, right? You got to define the distribution. This is how we define the distribution. So we want to find the probability that x equals 3. Well, that's pretty easy. We're going to take e to the negative lambda to the third over 3 factorial, which can also be done, like we've said before, by using a PDF, Poisson, PDF 1.25 and 3, okay? In either case, you'll get the probability that exactly 3 of them showed up during the first hour. I'm going to do that right now, PDF 1.25 and 3, and our answer comes out to be, let's see here, to 3 sig figs, 0.0932. There you go, guys. About a 9% chance that 3 of those folks came during that first hour. That's Poisson. See you in the next video.